Donc c'est une matinée qui est assez diverse dans sa composition. Et nous allons commencer sur... enfin, il y a d'abord monsieur Zajfman, qui, comme vous le savez, est professeur de physique. Il a préparé sa thèse de physique au Technion. Et il a été élu, très jeune d'ailleurs, président de l'Institut Weizmann, qui est un des plus grands instituts de recherche au monde et qui est marqué par une grande interdisciplinarité, en même temps que par une inclination pour les recherches pour l'innovation. Et ça, c'est probablement une de vos contributions, monsieur le professeur, récente. Donc, et comme c'est aussi un institut qui défend et qui illustre magnifiquement la recherche fondamentale, je crois que nous allons avoir un éclairage très intéressant sur la liaison qu'on peut faire entre recherche et innovation, que l'un n'est pas l'ennemi de l'autre, bien au contraire. Voilà. Donc, merci beaucoup d'être venu et nous sommes impatients de vous entendre.
Merci beaucoup. You'll excuse me, but I'll do that in English. It's just much easier for me, même si mon français est capable quand même. Si vous posez des questions en français, je comprendrai. I'll try to, during this lecture, to provide you an insight about how we, scientists dealing with fundamental science, is looking really at what the secret of nature is all about. Looking not only at how we should make or how we are trying to make progress, and I'm really talking about all field of sciences. I'm talking of everything from pure mathematics all the way to, biomedical research, including chemistry in the middle, physics, computer science, whatever you want. How we try to look at one of the best ways to make progress in these fields, and at the same time really to translate these discoveries into something which everyone expects from science, which is really an impact on humanity, an impact on society, creating new drugs, new technologies, basically make the life of everyone better. And I think there should be no doubt in the mind of the people sitting here, and I guess those who are not sitting here, that indeed, if there is one factor that has changed the way that human society is living for the last hundreds of thousands of years maybe, but certainly for the last 100 years, it is a scientific discovery. The way we live today and the way we lived 100 years ago, let's say, the difference between these two is mostly due, in fact, to the advances in science and technology. Just to remind you, 100 years ago, the average life expectancy would have been 40 years, meaning, excuse me, but for most of the people here, that none of you would have been here, actually, except the ladies were always younger. While today, average life expectancy is actually close to 80, 82. And the major change, of course, is due to the knowledge we have acquired over the years about what nature is all about and how we can improve our situation on this planet. And that is done mostly through research and, of course, mostly through scientific research. Now, one of the things that people like to do is always to try to speak about the future and try to make prediction about where will the world go, or where is the world going, and what are we going to use in 10 years, 20 years, sometimes even believe they can make predictions for the next 100 years and how the society will look like in 100 years from now. So I just want to remind you about, just as an example, about some famous sentences that scientists actually made and people who are knowledgeable about science. For example, this one about a very famous scientist, Lord Kelvin, really a mathematician and physicist back in 1895, who made a very famous statement saying that heavier than air flying machines are impossible. He's not just anyone, he's a physicist, he's a scientist, and you can see how wrong he can be in his own predictions. So it's not someone who doesn't know physics, it's someone who knows physics in 1895 and make one of the wrongest predictions you can dream of. And so you can see how complicated it can be. Or for example, you can go into something even closer to the time of today, when Ken Olson, one of the director and CEO of a major computer company that used to exist and was competing with IBM, called DEC, Digital Equipment Corporation, which back in 1977 said there's no reason anyone would want a computer in their home. That's not even a scientific prediction, it's a technological prediction. And 6 years later, I had a personal computer in my home. 6 years. This guy is supposed to know something about computer science, and yet he has no idea where these things are going. And of course, today, this company doesn't exist. But what you see are two examples, and clearly there are thousands of examples like these. One of them is really almost on fundamental science, so misunderstanding of what science can do, and the other one is even when technology exists already. Computer did exist in 1977, yet nobody really knew and understood the impact of them. Now, we all kind of remember all the right predictions, because that's the one our human memory like to remember, but and that's how we believe that most people can, or most smart people can make predictions. But the truth of the matter is, predictions are very, very complicated, especially for the future, of course. So the point is, we should not try to make predictions about where science is going. We don't really know, and once we agree that we don't really know where these things are going and what we can do with it, the question really is, then how do we do research if we don't know where to go and what is possible and what is impossible? So let me first give you a very simple scheme, an oversimplified scheme, a very, very simplified scheme of the connection between science and technology and research and development. On one hand, we know about scientific research, namely people, like here in this institution, people going into the laboratories and trying to discover the secrets of nature. And we also know that what drives most of these scientists of trying to understand the secret of nature and filling what I call the reservoir of knowledge, a bucket, which is what sometimes the feeling we have as scientists when we are learning and publishing papers, we are adding to the society bits of knowledge which accumulate in different reservoirs and different buckets. And it's not a simple one. There are really thousands and millions of buckets like this. And then we hope that once the bucket will be full, it will lead to some new ideas and some applications which could go into the industry. And of course, the industry would know what to do with it because the industry knows the market. And if there is a market, then we can develop a lot of technologies and products. So this is clearly a very much oversimplified pictures of how science is working. Very, very often, on one hand, the industry would create products we don't need, and there's a huge market for it, yet it's possible to do it. And on the other hand, there are products that have been developed without scientists even knowing why they work. I can give you two examples. One of them, for example, is a steam machine, which was developed without us really understanding thermodynamics, which is the basis of physics or what thermodynamics does and how steam machine is working. It took 50 years between the Industrial Revolution in the UK and the French physicist Carnot to really understand the process, yet the machines were working before we understood. Or for example, many of the drugs one is using today, we don't really understand all the basis of their function and why they're actually curing. Of course, we don't care. As long as you can cure disease, why should we care how it works? But this scheme is really oversimplified. It doesn't always work from the very fundamental scientific research all the way to the technology and product, yet it is an overall scheme that, we can't, it's very hard to make product without having the fundamental knowledge. But I want to make clear that it's not a simple way to go, and there are loops all over the place. But the first question is, what makes scientific research filling the bucket? I mean, what really drives the initial step? And for many of the scientists, at least for people like myself and many people in this institution, I think it is actually curiosity. As I'll show you, it's not the fact that the people doing the scientific research know something about the products that need to be produced. It is simply their own curiosity that fills this bucket. And it's a very interesting way of looking at how from human curiosity we can create something which is actually useful without even knowing that it could be useful one day. And that's what I'd like to focus on. So, to give an example from a totally different field and, of course, unrelated to scientific research, Donald Rumsfeld, when the Secretary of Defense during the Iraq War in the United States, made an interesting statement about weapons of mass destruction. But, I translate that into the field of scientific research. Somehow it works, somehow, saying that there are known knowns. These are the things we know that we know. And, that could be very useful as well in research when you do improvement. There are known unknowns. That is to say, there are things that we know we don't know. We realize these things exist. We just don't know how they work and why it happens like this and, and how can we improve them and so forth. And then, of course, the most important things and interesting thing in science are the unknown unknowns. These are the things we don't know, we don't know. And the question we should ask is, how do we discover things we don't know, we don't know? There's a tendency of people believing that we, the scientists, know everything. And I can tell you as a scientist, we know nothing. We know very, very little. And the question is, how do we discover what we don't know that we don't know? That's a very complicated question. And there's really one answer to it, and almost a unique answer to it. And that's a human curiosity. And I'll show you why and how it works. So how to discover the unknown in unknowns is the question we're asking. So let's try to see some historical example, and then I'll show you some very modern examples that you're using every single day, and you'll see from where it's coming and how these things are coming together. It is always, of course, better to use example than to try to make a theory about it. I'm sure you'll agree with me that X-rays are very useful tools every time you go to the dentist or whatever medical check you have to be going through. When you do an X-ray, and that X-ray allows you to look at your bones. X-rays were discovered by a scientist, a physicist, Röntgen in Germany, back in the 19th century. We did some very, maybe I would call this boring experiment. They're not boring for me, but for many people. Not something you would find, and not something you would write a proposal about. Not something you would believe could lead to something interesting. It was simply measuring how electrons were moving from one electrode to another one in a tube filled with different gases. And when looking at the curves of, on one hand, current, and on the other hand, the voltages, and was making graphs as a function of the pressure, and looking at all these very, very interesting data, for which nobody really outside of his lab, and perhaps few other physicists would have an interest in, and certainly nobody would have found that. Then, of course, one day he discovered something very strange in his lab, which is some scintillation, some light on the wall. And because he was a very curious scientist, and knowing that even he had a plan to measure these things, you always have to have an open mind. He looked at it, switched off this instrument, switched it on, tried to see from where the light was coming, covered the whole instrument, and discovered to his amazement that even when he covered the whole instrument, the light was going through the cover, which is, of course, unthinkable. I mean, how could you think that light would go through something which is, dark and opaque? And of course, what he did, the first thing is, what every man that doesn't know what he's doing is calling his wife and putting her hand in front of the radiation, and discovered that he could see the bones of his wife. You can even see the wedding ring of her on her finger. Now, you would call this chance. He was lucky. Indeed, he was lucky, and for a scientist, the talent to be lucky is a very important talent, clearly. But one has to realize a few things here, that nobody would have discovered the X-rays if it wasn't for someone doing this kind of boring experiment. The second thing is, these experiments were actually made before him. Other people have done this. It's not the first time that an experiment like this was done, yet nobody saw these X-rays, even though they existed in the lab of other scientists before as well. So what made him discover the X-rays is not that he did a unique experiment. It's not that he was the smarter the scientist. It was that he had an open mind and had the freedom to look around and diverge from his original plan to ask important and interesting questions and find something that was unusual, and the word unusual is important, and take action on it. And that's, of course, the kind of scientist who can make important discoveries. What I mean by that is that there are no scientific strategies or scientific programs. You could not write a proposal. You could not get funding to discover X-rays because nobody knows that X-rays existed at that time. So this is one of the answers. How do you discover things you don't know? There's no way to propose to discover something you don't know. And the only way one can do that is by having outstanding scientists, and by outstanding I include the fact that they have to be very curious and open mind, to do relatively simple experiment, if one can call this a simple experiment, but allow them to really follow their own curiosity so that they can actually find things happening in their laboratories which are unique and have not been seen before, and you don't know ahead of time. So this is one example of how by not controlling really the output, one can allow outstanding people to make very, very important discoveries. And you would agree with me that starting from very fundamental sciences, measuring the currents of electrons, and moving to X-rays in one day is a very quick move from fundamental science to application. So, sometimes it's not a long-term planning, and actually there's no marketing here and whatever, and nothing else in between. So this is, again, an important part. Here's another example, a little more modern, one that you're using today every day. I'm sure you all know, and using your GPS on your car or anywhere else in order to find your way to come to the very busy streets of Paris or all over the world. And you all know that in order to do that, you need to get a signal that comes from satellite, which is satellites, many satellites orbiting Earth and sending these signals to your little device, collecting these and making analysis of these signals so that you can actually, or the device can locate itself compared to all these satellites. These satellites were launched back in 1978. This is the beginning. You should know that in every single of these satellites, there is more than one, actually two sometime, atomic clock. And the first atomic clock were developed around 1955. Now, clearly those who back in 1955 created the first atomic clock had no idea that one day this atomic clock would be located into satellites, which would be used to give you a signal on which you can find your location. Now, this atomic clock and all the science behind this would have not been possible if it wasn't for Isidore Rabi, another physicist who back in 1945 discovered what is called the magnetic resonance, which is another quantum phenomenon that happens in atoms, which is a very fundamental one and is related to the way, if you want, atoms are spinning around and the way that the quantum states are separating. Now, you realize there's absolutely no connection between Isidore Rabi, magnetic resonance, atomic clock, the GPS satellite, and your device. But you should also know that your device would not work properly if it wasn't for the theory of relativity of Einstein, both the special and general relativity, which back in 1905 and 1915, just out of pure interest, wanted to understand how the universe, if you want, is structured and developed this theory of relativity. Einstein had no idea about GPS, you realize this. Now, and of course, nothing about atomic clock, and certainly not the satellite. There was no satellite during his time. Yet he developed the theory of relativity. The whole GPS story goes back more than about 100 years to the relativity, but there's no connection. Now, it's very easy for us to look at this backward in history, to see, oh, all these people developed all these steps so that today we can use the GPS. But think about it forward. Try to understand, can actually Albert Einstein or Isidore Rabi or the people behind the atomic clock or even the satellite know that one day this will be used for this kind of technology? Of course, there's no way. There's just no way to make any prediction about what we would do with a very, what people call a complex, sophisticated theory of the universe that one day will be located in our device and will create a market of $1 trillion because today, location market, everything driven by GPS, as we know today, is a huge market, and you can make a lot of money out of it. I guess Albert Einstein would flip in his thumb if he knew how we use the theory of relativity today. So you can see how complicated these things can be and how complicated it is to make a plan about where science would be and maybe how much of a mistake we do when we try to make a plan. I'm not saying no planning. I'm not saying that there should be no planning, but this is one of the best examples, and I could really go a long way. So this is another way to look at this. There's no chance here. There's no serendipity. It's not like Röntgen discovering X-ray. It is well thought, but nobody thought about the whole map here. It all happened, if you want, out of itself because we have these technologies at hand. And the last way to look at this, at the unknown, is to try to understand this, I would say this way we have of doing research, or when we know a technology, all what we're looking for is to improve it. Maybe one of the best examples is to go back 200 years ago. So when one of the best ways to have light inside our homes and maybe sitting here would be to light up a candle. That was the way for making light in the home. And there was a lot of R&D on candles. This was a very important technology. Everyone wanted to improve it. Maybe a bit like the electric car of today. We have batteries, and we try to improve batteries so that every year we can drive a little more. 150 kilometers range, 200 kilometers, 220, 230, very important research that allows us to create better and better batteries and better electric car. Back in 200 years ago, it was better and better candles so that we can have more light, cheaper one, different colors, different perfume, whatever you want. Very important research, which of course, years after years, would improve the quality of the candles. And then of course, one day, Michael Faraday, among some other people, arrived, and he discovered electricity. Now, I want you to think about that. It doesn't matter how much money you're going to spend on developing new candles, you will never find electricity to that process. It's not because you're investing in the technology that exists today, and you know you can improve it, and you can improve it, and it is important, that you will make the discoveries that are changing the world. Sometimes it is located on a different table, in a different home, in a different place. And this is another problem that research is facing, and the more and more we're focusing on trying to update our existing technology, something we should do. I'm not saying we should not do. The more we do that, and the less we do the kind of curiosity-driven research, the less we will be able to make these discoveries that are actually making a revolution. And you'll see that in a minute, the difference between evolution and revolution. All right. The last example I want to give you is something that most people don't know, and it's not history anymore. It is what is happening today. Everyone is worried and wanted to get new drugs. Curing disease is becoming the disease of the world, and we all understand why. It is very important to create these new drugs. People suffering and being able to cure cancer, Alzheimer's, Parkinson, all these diseases. We have no treatment for it, or improving all of them, of course, is important. Here's a paper published just last year in Science Translational Medicine, and try to make an analysis of the science, or what they call the fundamental science, behind today's important medicine, the drugs we're using today. So here's a table. I know you can't read it, but you have to believe me. There are 28 drugs that are the most drugs used in the world. Okay, this is what these drugs are all about. And the first, and probably need my glasses if I want to read it myself, and the first column tells you the origin of the discovery. And the first column, where it's written yes or no, is telling you if the origin is in basic discoveries. And the answer is that 23 out of the 28 drugs were made by fundamental discoveries. What it means is the second column. The second column tells you is the origin where basic discoveries, where the discoveries disease-oriented, meaning where the scientists are actually focusing on the disease that the drugs today are actually curing. And the question is, 16 out of 28 were non-disease-oriented research. Nobody paid these scientists to create a drug for curing any disease. It was actually based on fundamental discoveries. It was not disease-oriented. Even better, where early discoveries made as a part of a drug discovery program. We have huge drug discovery programs where we're spending billions of dollars for developing new drugs. 23 of these drugs were not part of a drug discovery program. The vast majority of them were discovered not from programs that were funded for discovering new drugs. This is the difficult part. The time lapse from the basic discovery to the market is on average 30 years. Some of them, by the way, is 60 years. And I know even a drug, it took 100 years to bring from fundamental discovery to the market. But that's the reality of the 28 most used drugs in the world. If you look at the bottom line here, the vast majority, if not almost all of them, were not part of the drug discovery program. This is mind-boggling. Yet everyone keeps spending lots of money on drug discovery programs and trying to find drugs for curing specific disease and engaging billions of dollars for thousands of people focusing on developing a new molecule to cure one single disease. Now, I'm not saying one should not do it, but I'm just saying we are just overdoing it. That's what I think we're doing, and that's 2018. This is not 200 years ago. It's not that science has changed. It is the same story. And I think people don't see that. I think people don't look at this and don't look at the data. And as scientists, we should take the data and based on the data, make our